Hello students, welcome back to our channel. Students, in this video we are going to study a very important topic from class 11th physics, and the topic is simple harmonic motion. In short form it is called SHM, and it is one of the most important topics in class 11th and 12th physics. So let's start. What is a simple harmonic motion? A simple harmonic motion or SHM is defined as a motion in which the restoring force is directly proportional to the displacement of the body from its mean position, and the direction of this restoring force is always towards the mean position. Okay, what is a restoring force? What is SHM? What is all that is written here? We will understand each and everything. Okay, first let us understand the meaning of the term restoring force. A force that brings a body back to its stable equilibrium position. Students, there are three types of equilibria. When a body is at rest, it can be in any of those three equilibria. First type of equilibrium is called the stable equilibrium. Let us consider a situation in which a ball is placed in this depression. This is a depression on the ground or anywhere, and a ball is placed on the lowest point of this. Suppose it is a pit in the ground and this ball is placed at the lowest point of this pit. Now if this ball is displaced from this position in either direction, if I'll displace slightly this ball slightly towards right or towards left, what is going to happen? Now if I displace this ball slightly towards right, then it will go up, and when it is going in the upward direction, then obviously the speed of the body will decrease because gravity is pulling this body in the downward direction. So ultimately the speed of the body will become zero and it will again come back to its position. But since it has gained momentum, so it is not going to stop in this position. It will go in the other side, it will go on the other side, and then again the same thing happens. When it is going towards the left side, it is getting slow, and here it stops and then it comes back again to this position, right? So what is happening? This position is the position of the stable equilibrium of the body, because when the body is displaced from this position, the body is again trying to attain this position, and that is the stable equilibrium. Stable equilibrium is a position from which if the body is displaced, it will again either come back to that position or it will try to attain that position. This body will eventually come back to this position and will come at rest on this position because there is ground friction, and ultimately this motion is going to stop after some time and this ball will be here again. So that is the position of the stable equilibrium. Okay, now suppose this part of the ground has this shape. Now if you place a ball very carefully, not this ball, suppose we have any other ball. If you place a ball very carefully on the topmost point, then it will be at rest. But if you displace this ball slightly from this position, it is not going to come back again to this position. So this type of equilibrium is called the unstable equilibrium, in which the body is in equilibrium right now, but if it is displaced from that position, it is not going to come back again to that position. That is called the unstable equilibrium. Unstable equilibrium. Number 3 is the neutral equilibrium. Now consider this flat part of the ground, and if the ball is placed at this point, now if you displace this ball slightly, it will go to this point and stop here. It is not going to come back to this position, right? And what is the difference between the unstable equilibrium and neutral equilibrium? In neutral equilibrium, ball was not going to come back to the position of unstable equilibrium, and when it will go somewhere, we are not sure whether it will be at equilibrium or not. But in neutral equilibrium, we know that the ball at this position is at equilibrium, and if it is slightly displaced from this position, then again it is going to come to another equilibrium position. So this type of equilibrium is called neutral equilibrium, right? So to perform simple harmonic motion, the first condition is a body should be placed at the position of its stable equilibrium, right? So when we displace the body from its position of stable equilibrium, it will try to come back to that position again, and while coming back to that position, it will gain some momentum, and that momentum will not let the body to stop at the equilibrium position, and it will go towards the other side of the equilibrium position, and with this the body will start doing simple harmonic motion, which is just simply an oscillatory motion to and fro, left or right, back and forth, anything can be said about the position of stable equilibrium of the body, and that position is called the mean position. So this body will be doing like this, and this pendulum, this is the position of the stable equilibrium of the pendulum. So it is, if it is displaced towards either side, it is going to come back, and then it will go to other side, and it will start performing simple harmonic motion. So in simple harmonic motion, the restoring force is directed towards the mean position, and that force is provided by some other force that is present at that time. For example, in both these cases, in this case also, in the case of pendulum also, the restoring force is provided by what? It is provided by the gravitational force. If the gravitational force is not there, this body is not going to come back again to this position, or it will not going to get slow, or it is not going to stop eventually. It will, if you displace it slightly and there is no friction, there is no gravity, the body is going to jump over this hump, and it will go towards the neutral equilibrium position, right? So we are not talking about those situations. So let us say that gravity is present, right? So if gravity is present, obviously the gravity is responsible for bringing this body back towards the mean position, right? So the gravity is providing the restoring force. So any force which is bringing a body back towards the mean position, or if it is trying to bring the body back towards the mean position, that force is called the restoring force. And in simple harmonic motion, or a motion is called simple harmonic if the restoring force is directly proportional to the displacement of the body from its equilibrium position, right? When the restoring force is directly proportional to the displacement of the body from its equilibrium position. For example, suppose this is the equilibrium position of the body. Let us take an example of a block which is connected to a spring. It is a very good example of simple harmonic motion. Now let us say there are two blocks. There is one block. Why I am taking two blocks? Okay, there is a block which is connected to a spring. This block is connected to a spring. Now if you will pull this block, towards the right and release this block, it is going to do oscillatory motion like this. Okay, suppose we have pulled this block towards the right, and from its mean position, this is the displacement of the block. from its mean position, this is the displacement of the block, this, and this displacement is x. So we know that when what is the displacement vector of a body or the position vector of a body? Let us say that the mean position is the origin, right? So when this body is at this point, this will be the position vector, or we can say the displacement vector of the body, and this will be the direction of the restoring force. So because restoring force is pulling this body back towards the mean position, na? So this is the direction of the restoring force, which is obviously opposite to the direction of the displacement vector. Now if this body going towards this direction, and suppose it is somewhere here, now the displacement is like this, but the restoring force is like this. So restoring force and displacement both are always in opposite directions. That's why we have put a negative sign in this formula. But one thing is to be remembered, that the restoring force is always proportional to the displacement x. More is the displacement of the particle from the mean position, more will be the restoring force acting on it, and in the opposite direction. If the oscillatory motion is satisfying both these conditions, then we are going to say that this body is performing simple harmonic motion. In every type of simple harmonic motion, whether we will take the example of this spring or pendulum or in any other case, that motion is called simple harmonic motion because it is satisfying this condition, right? So when we will remove the proportionality sign, we are going to put a constant, and that constant is k, and that is called, k is called the force constant, right? K is called force constant. So any body which is satisfying this equation during its motion is obviously performing simple harmonic motion. And simple harmonic motion, all simple harmonic motions are periodic in nature. A periodic motion is something which is getting repeated after a fixed interval of time. For example, the motion of Earth around Sun is periodic in nature because Earth takes a fixed time to complete one rotation around Sun, and that is 365 days 6 hours. So we can say that the motion of Earth around Sun is periodic in nature, but that is not oscillatory. So all oscillatory motions, or all bodies which are performing simple harmonic motions, they are performing periodic motions. For example, if the external forces, external resistive forces like air friction, ground friction are neglected, then the time period of this simple pendulum or this body connected to the spring is going to remain same for every oscillation. What is time period? Suppose this pendulum is displaced from this position. Now it is starting from this position. So the time it will take to complete one oscillation. What is regarded as one oscillation? When this body, when this pendulum is going towards right, then it is coming back again to the mean position, then it is coming back, going again towards the left to extreme position. These two positions are called extreme positions, from where the body is going again going towards the mean position. The velocity of the body at the extreme position is 0, because when it is going from mean to extreme position, the restoring force is continuously pulling the body back towards the mean position. So it is getting slower and slower and slower, and finally it stops and it comes back to the mean position, and this position where the velocity becomes 0 is called extreme position. So the body starting from the mean position, going towards the one extreme, then coming back to mean position, then going towards the other extreme, and then coming back to mean position. This makes one complete oscillation, and the time this body takes to complete this one oscillation is called the time period of oscillation, right? So in SHM, the time period remains constant when the external forces are neglected. So we can say that the simple harmonic motions are periodic in nature. Okay, there is one very important thing to mention, that the displacement equation, why is the displacement of this body from the mean position, or we have we have taken it as x, right? Generally, if we are finding the displacement of the body from mean position, then we take it as y. This is the notation. And if we are finding the displacement, we are taking the displacement of the body from the extreme position, then we call it as x. So in all the examples, we are taking the displacement from the mean position. So to make uniformity with the books, let us take this as y, not x, right? This also. So this y, the equation of this y is a sine omega t. This equation will help you find the position of this body in time t. The displacement function of this body is sinusoidal, right? So this is also a sign that the body is performing SHM. Why this is sinusoidal? Because if we draw the graph of the position of the body with time, we are going to get a graph like this, right? Because first the body is going towards one extreme, then it is coming back to mean, then it is changing its direction and going towards the other extreme, then again coming back to mean, and it is repeating this motion. So if you will draw the graph of this, you are going to get this graph, which is exactly the graph of the sine function. The only difference is this: sine function goes, the maximum value of sine function is 1 and the minimum is 1, but this is going to have a maximum value of its amplitude A, and the minimum value is also the amplitude on the other side. Amplitude is the maximum displacement of this body from the mean position, which is denoted by A. So if you find the position of the body, if you want to find the position of this body at any instant, you can put the value of that instant in this equation and you will get y. And here omega is called the angular frequency of the motion, which is 2 pi divided by t. Here t is the time period of oscillation. Okay. So what are the important characteristics of SHM? I hope we have discussed all the characteristics. Simple harmonic motion is a special case of oscillation along a straight line between two extreme points. Between two extreme points, the body is moving. According to Hooke's law, F equal to minus kx. The name of this law is Hooke's law, which is a very important law in mechanical properties of solids. So you don't have to remember the name for SHM. You just have to remember this equation, and you have to know the meaning of this equation and the meaning of each and every term involved in this equation and the significance of the negative sign. A periodic motion repeats itself at regular time intervals. We know this. In oscillatory motion, the particle which is doing the motion, the particle motion is to and fro about a mean position. Yes, in oscillatory motion, the particle motion is to and fro, up and down, back and forth, and there will be a restoring force directed towards the equilibrium position or mean position, right? So this was the introduction of simple harmonic motion. We have seen the meaning of the term SHM, the important equations, the conditions, and everything. So I'll meet you in the next lecture related to this topic. Till then, all the very best.